Hello, and thank you for tuning into this presentation. And thank you as well for your interest in instrument modeling, which we think is very important for getting the best results in applied optical metrology. This is actually the third in a series of papers we've been giving at the SPIE Annual Meeting, starting in 2019 with the paper, Does Interferometry Work? Fortunately, we found out that it does. But we also emphasized in that paper that it's important to think about interferometers for surface topography measurement as imaging systems. So last year in 2020, we presented a simple Fourier optics model for monochromatic interferometers to help understand potential errors and other performance characteristics using traditional Abbe theory. Today we'd like to show you how this model can be extended to coherence scanning interferometry, which is currently the most popular technique for 3D microscopy using interferometry. As you'll see, we'll find that a simple model of this kind can be very useful as a first step in understanding coherence scanning interferometry. You can calculate things like the instrument transfer function and so forth. But our work also provides clear guidelines, we believe for the first time, for the range of validity of such simple models and when more accurate techniques such as 3D transfer functions should be employed. So with this introduction, I'd like to go ahead and get started. Walking through the outline, we'll begin with a brief description of coherence scanning interferometry, how it works, and how a Fourier optics model can be constructed for CSI that's pretty easy to implement and at least gives us a start in understanding how these instruments function. We'll talk about some of the limitations and show some clear boundaries for use of a Fourier optics model and when you need a more advanced model, which will be the next topic. Some overview of what an advanced method looks like that uses the 3D nature of the problem as a foundation. And then finally, some perspectives and future work. People have been using interference fringes for a long time to look at surfaces and wavefronts. Here's a simple example of a light box where you can see these interference fringes. The fact that these fringes are not straight tells you something about the difference between the surface form of the object, which is on the top, and the test plate, which is on the bottom. So you usually assume the test plate is perfect and the object is on the top, and you use the shape of these fringes to tell you something about the topography. By far the most common way to describe a surface topography, at least today, is a surface height function. So you have this h as a function of x and y, where x and y are the in-plane lateral coordinates. So how do we measure this topography in an interferometer? So here's a configuration that ought to work. We have some imaging optics here. We got a light source, light's coming from the left. It's split up between the reference mirror and the object, and those two reflections get combined back at the camera, and that's how we're going to get our interference fringes. So let's suppose that we have the object positioned on a scanner, and we have a light source on the left-hand side that is spectrally broadband, like a white light source and white light LED, something like that. Then when we scan the object up and down and record the results on the camera at the top, then we see an interference pattern that looks like this thing on the right. In cross section, you can see interference fringes that are appearing that kind of mimic the profile of the object. The spacing between those interference fringes is about half a wavelength, and the fringes are localized. They're localized because of a coherence effect. If you take that interference pattern for just one image pixel, you can extract a signal, what we sometimes call a pixel trace, on the right-hand side. And you see an interference pattern which is modulated by a coherence envelope, and there is a peak position, the coherence peak. At that point, the group velocity optical path difference between the object leg and the reference leg is 0. So you have this interference pattern and you have this coherence envelope. Both of those things are quite useful for determining what the surface height is at that point. If you take that interference signal for each image pixel and you do an analysis of fringe phase and the coherence peak, you can use one or the other or both to get this surface profile that you see here. And a lot of instruments work that way. They look for that coherence peak in one way or another. They demodulate the fringes to look for the coherence peak. And then they analyze the interference fringe phase, maybe using a phase shifting algorithm on each pixel. But there are other ways to do this. An alternative approach to getting surface topography information from CSI data is to take the data and transform it into the frequency domain. And then you get frequency domain analysis, or FDA. So the way this works is you take that signal, you do a Fourier transform, and on the right-hand side, you see the Fourier coefficients in terms of magnitude and phase. Now the magnitude, you can see, has sort of this bell-shaped curve as a function of fringe frequency. So that's how fast the interference fringes are going by as a function of scan position. And there's a range there because you have many different interference frequencies present because of the broad spectrum of the white light source, and also because of the range of incident angles on the part at high numerical apertures in a microscope. That's the Fourier magnitude. Now the Fourier phase is even more interesting because this is going to tell us what our surface heights are. So if you look at the signal as you change the height, you can see that the signal is moving to the left and right, but also the Fourier phase in the right-hand side in the frequency domain is changing. So the slope of that curve, the rate of change of phase with fringe frequency, is changing, and also the offset of that curve is changing. And those two things are going to tell us a lot about what the local surface height is. To take advantage of the Fourier phase, what we do in software is we pick 3 to 5 values near the peak Fourier magnitude. And we look at those phase values and fit a line. And from that line, we can extract a slope. That's the rate of change of phase with fringe frequency. And this is called the coherence profile. So this is now a standardized term. And this is very similar to finding the peak of the envelope. That slope is indicative of where the signal is located. But the next thing you can do is you can look at the phase offset, and that provides the so-called phase profile. So you've got these coherence profiles and phase profiles, and the phase profile is just the phase at the peak value or the peak magnitude of the fringe frequency. Now the coherence profile is best for rough parts. So what do we mean by rough parts? Like machined surfaces and additively manufactured surfaces. So why is that? Well, that's because the location of the signal is something which you can find even if the interference fringes are pretty confused, which can happen on a rough surface. So that's the big advantage of a coherence profile. If you have a smooth part, maybe it's an optical component of some kind, then you're probably better off using the phase profile. With the phase profile, you can get very low noise levels down in the tens of picometers if you've got the time to take the data and average it. And the phase information is known to be much more precise, but in interferometry, it's also known that you need to resolve the fringe order or figure out which interference phase order you have. And that is often done in CSI using the coherence information or the coherence profile. Now that we've covered coherence scanning and interferometry, let's go back to our outline and tackle the problem of modeling the kinds of signals that we expect to see with CSI. The most important first step in a simple Fourier optics model is representing the surface topography in a way that allows us to use two-dimensional Fourier transforms, even though it's a 3D object. And the way we do that is we describe the height as a function of xy as a phase variation. So we effectively encode the heights as phase shifts in a complex valued flat object. So that's this equivalent thin phase object that I've shown on the right-hand side. And the phases are proportional to 2 times 2 pi times the height divided by the wavelength. And then there's an additional factor called the obliquity factor that has to do with the geometry of illumination. So this step is taken all the time in interferometry, and we don't consciously realize what we're doing. But it really is actually kind of profound, because what we're saying is even though the object is 3-dimensional, we can represent it in one plane as a complex object, actually a complex wavefront that's reflected from the object surface. With this approximation in hand, we can now apply scalar diffraction theory, and we can propagate the spectrum of plane waves into the far field. After the incident light is scattered by the object surface, an optical imaging system will collect this light and image it onto the camera. And of course, this process is imperfect. There will be limiting apertures in the optical system, And some of the high spatial frequencies, some of the steeper angles of diffracted light will be blocked. And in a conventional optical imaging system, we calculate that using, for example, an optical transfer function. So this is a familiar way of calculating the optical transfer function. And gradually, as you go to higher spatial frequencies, steeper diffraction angles, you find that the light is blocked. If you work through the effects of a Fourier optics model of optical imaging on a surface topography measurement using interferometry, you end up with this EFO model, or Elementary Fourier Optics model. And this is described in detail in last year's talk if you'd like to see. There are some online tools. This is from zygo.com or researchgate.com. You can download this Excel spreadsheet and you can play with this thing and you can see what the effects are of changing the imaging numerical aperture, changing the amplitude of a sine wave, or changing the period of the sine wave and so forth on the final result. And the key message is that because of those limiting apertures and the loss of some high spatial frequencies, there is an effect on the final surface topography measurement that you can predict. So this was for monochromatic interferometry. That's what we described last year. The next question is, well, how do I take this simple EFO model and apply it to coherent scanning interferometry, which has more wavelengths than just a monochromatic system? The easiest approach to applying an EFO model to CSI is to simply repeat the model for each of several wavelengths. And in this approach, what we do is we associate each of the wavelengths of the light source with a fringe frequency. And then we bundle the effect of different angles of incidence on the part into a single obliquity factor, which is actually it's a familiar technique to use in interference microscopy. So the fringe frequencies correspond to wavelengths, and we take a handful of them, enough of them, to calculate those phases that we use in frequency domain analysis, or FDA. So it's really not too much more complicated than the EFO for monochromatic light. Now, in the procedure that I just described, you get directly the surface topography without actually synthesizing a CSI signal along the way. But there are times when you would like to actually simulate the signal. And for that, you can take the data that you've calculated in your simulation, and you can add a z-axis propagator for each wavelength, meaning each one of the Fourier components. And then you add those things up in an incoherent superposition, and you end up with the fringe pattern that you see here for a rectangular shaped object. And this has all of the features that you expect from a CSI signal. So why would you want to do this? Well, it's useful for visualization. Makes a nice picture, I think so. It's also good for testing analysis methods that are not based on FDA. So if your method of reducing CSI data for surface topography does not involve FDA, you're doing envelope detection or some other method, correlation method, then simulating the signal and using this procedure is a very useful thing to do. So let's take a look at some simulated topography measurement results. And we'll start with a rectangular profile measured with a 5.5x objective. So the numerical aperture for this objective is 0.15. We'll take a wavelength of 0.57 microns, which is sort of greenish light, and the full width at half maximum, so that's the spectral bandwidth of the light source, of 0.12 microns. And the height of this rectangular feature is 3/4 of a micron. Now, if you measure this thing with CSI, you will get that object surface profile, but you will get a little bit more than that. So I'm going to show you what the errors are in that measurement, or what the errors at least could be. I mean, every software package is going to behave a little bit differently, but you can expect to see something like this. In the coherence profile, you may actually get some fairly large, what are sometimes called bat wings, or overshoots and undershoots, that relate to the fact that you have very sharp edges. And those sharp edges in the object surface profile generate a lot of high spatial frequencies, which as we've seen, are blocked by the limiting apertures in the imaging system. And that's why you get this type of an effect. Now the error is a little bit more than 10 times smaller for the phase profile, as you can see in the lower right-hand corner. So this is one of the reasons why the conventional advice in CSI is to use phase information, use the phase profile or the high resolution measurement as much as you possibly can, unless you just can't get it because the surface is too rough. But this is definitely a case where the phase profile is much better than the coherence profile. And we see that already in this simple EFO model of CSI. The next simulated profile that we'll look at is a sinusoid. We'll look at it with the same objective and almost the same light source. And what we find is that the error in the measurement when you're done is not quite so dramatic. So this is the coherence profile error. And this is more like 20 nanometers instead of 200 nanometers like we saw in the previous slide with the rectangular object. And the interface profile is also better here, but not quite so dramatically better. If we repeat the simulation over a range of sinusoidal spatial frequencies, we can generate a graph like this, the theoretical instrument response, as a function of spatial frequency. So the instrument response is the measured amplitude compared to the known amplitude of a sinusoid. And this has been verified experimentally. For example, at the 0.125 inverse micron spatial frequency, you can get a material measure an actual physical sinusoid. Look at that experimentally with a CSI instrument and you find a very good match to the EFO modeling. A common question is, what is the ultimate lateral resolution of a given CSI instrument? So as an example, suppose we have two trenches, center on center, 500 nanometer separation, and a center line that's just 200 nanometers wide. So if such things exist as physical artifacts, you can test this. If we look at the modeling at 100x, 0.85 NA, we find that those two trenches are resolvable. They are blurred, but they are resolvable. And experimentally, we see almost exactly the same profile, at least the shape. The actual depth is a little bit different because we're not including any polarization effects. But the shape is the same, and we do, in fact, resolve those two trenches in a real instrument. So the EFO model can be pretty good for this. So we've seen we can do a lot with this EFO model. What are the limitations? Under what conditions do we have to use a more advanced method? Elementary Fourier Optics modeling makes several geometrical approximations, some of which are quite severe. Starting with the notion that we can take a 3D object and represent it with a thin phase object, an object that has a complex reflectivity and a phase shift that corresponds to surface heights. But we make another approximation in this presentation where we say, well, we're going to take a single obliquity factor to represent the effect of all of the different incident ray angles that you have in an extended light source in an interference microscope. So that the question arises, well, what are the resulting limitations? When can we use this model, and when is it going to be not as accurate as we would like? We showed already last year that if you apply an EFO model to a fixed focus system like a monochromatic phase shifting interferometer, you'll get good results if you're at low magnifications and low numerical apertures. But as the numerical aperture increases, you start to have a difficulty with the depth of field, and the topography variation that you can accommodate starts to decline. So by the time you get to 20x, 50x, 100x, the range of topography heights that you can accommodate in an EFO model and get good results start to become quite small. But what happens in coherence scanning interferometry where you have a scanner where you're moving the object while you're acquiring data? Turns out there's some good news here. By virtue of the fact that you're scanning the object, you are always taking the data at the position of best focus. This is the coherence gating effect of coherence scanning interferometry. It's one of the benefits of coherence scanning interferometry. And we inherit that benefit in the EFO modeling work for phase-based measurements. Even at high NA, you can get pretty good results. A simple EFO CSI model that we've presented here, we've bundled together the effects of the different angles of incidence of the illumination into a single obliquity factor. And we lose a lot of information when we do that about how the focusing effects of the light influence the shape and actually the position of the coherence envelope. And consequently, we find in our theoretical analysis that you really can't have a numerical aperture greater than about 0.3 and get good results for the coherence profiles using a simple EFO model. So the accurate modeling in this case is limited to low NA values, unlike for the phase profile, which was much better. So if we want to really model the coherent scanning signal without these limitations, we need to move on to a more advanced approach. This brings us to the next topic in our outline, advanced methods using three-dimensional transfer functions. I showed this picture on the left early in the presentation, and interpreting the topography using the interference fringes is kind of based on a very simple idea, that the phase of the interference pattern is directly proportional to the surface height. The actual measurement geometry is in 3D. We have a range of incident light rays and a range of scattered light rays for each one of those incident light rays. So let's define a wave vector, k sub I, and a scattered wave vector, k sub s. So for every ki, there's going to be a range of ks values. And what we want to find out is, what are all of the different spatial frequencies generated by this combination of wave vectors? What are all the different ways that we can create an interference pattern? And what are the frequencies of those interference patterns? Here's the frequency domain image of that incident light wave vector. And that's going to span a range which is defined by the numerical aperture of illumination. So we have all these different incident ray vectors. For each one of those incident ray vectors, we've got a range of scattered ray vectors. That covers a combined frequency range that I've shown here. If you now sweep over all of the possible incident angles and all of the possible scattering angles for each one of these incident wave vectors, you end up with this type of construction, where the peak value, the maximum frequency along the z-axis, is 2 over lambda, and the maximum spatial frequency laterally is the Abbe limit. If you account for all of the different ways that these frequencies can be created by combinations of the ks and ki wave vectors, then you find that you have this transfer function. The transfer function has a magnitude which you can represent in a color plot, and you get this nice image that you see here. Now, a 3D model seems like a bit more trouble, and it is, but it's significantly more accurate, especially at high numerical apertures when you're looking at the coherence profile, because you're taking into account all of the focus effects. So here's an example where we've predicted the phase error using both an EFO method and a three-dimensional transfer function, and they overlap pretty well. And remember, I told you before that we have found that even at high numerical apertures, you can use the EFO model. But what happens at high numerical apertures with the coherence profile is we start to see differences. The EFO model is now underestimating by quite a bit the measurement errors that you expect to see in a coherence profile at high numerical apertures. And that's precisely because we've ignored all of the effects that have to do with high incident angles and high scattering angles. To learn more about how three-dimensional transfer functions work, you can download this virtual coherent scanning interferometer. This is free software from the Nottingham MMT website. You can also get it from the researchgate.com on Rong Su's page. We use this software extensively for evaluating the limits of simpler modeling like the EFO model, precisely because the 3D model is much more accurate, and it gives us an idea of what the ground truth should be. So we're approaching the end of the presentation, so let's consider what we've talked about today and what the future work might be. We hope that we've been able to convince you with these few brief slides of the value of instrument modeling and getting the best results in applied optical metrology. As we've seen, even a simple accessible model that's easy to implement can be of value. A traditional Abbe theory or Fourier optics approach can teach us a lot about how the bandwidth limitations in optical imaging affect a surface topography measurement. That said, another key conclusion of the paper is that at some point we have to take into account the focusing properties of these instruments in 3 dimensions. These are, after all, 3-dimensional objects that we're looking at, and a 3-dimensional transfer function is much more powerful in getting us meaningful results, particularly in coherence scanning interferometry, where the shape of the coherence envelope is so dependent on these focusing properties. The next step in the modeling is to take into account things like polarization, multiple scattering, reentrant features that you find on additively manufactured parts, rough textures, and other complex scattering situations. So this is ongoing work in instrument modeling. I'd like to close the presentation by saying thank you on behalf of my collaborators and myself, and I hope to see you sometime soon. We can talk about instrument modeling in person.